will be presenting part of our work that we are doing in our lab. And the title of today's presentation is the impact of graphene nanoplatelets on the buildability of fiber-reinforced concrete for additive manufacturing. The assessment of buildability of cement-based mixtures is especially useful for 3D printing applications. Buildability is the ability of the deposited layers to gain sufficient compressive strength to withstand the weight of 3D printed layers and is evaluated after the onset of initial setting. The structural buildup was characterized using the oscillation sweep tests, and we are using them to analyze the evolution of storage modulus, which is a 3D printable concrete should exhibit adequate storage modulus. The characterization of buildability requires the determination of material compressive strength at early age, also known as a grain strength. Grain modulus of elasticity is the slope of the linear portion of the compressive strength at early age, which is an indication of material stiffness. For additive manufacturing applications, high grain strength and modulus are highly desired. The polyethylene fiber-reinforced concrete for additive manufacturing advances and challenges. Polyethylene fibers are routinely used in 3D printing applications due to their exceptional mechanical properties. And they are using to overcome the brittleness of traditional concrete and to enhance the buildability by improving the material stability as it solidifies during printing. The challenge, though, of using PE fibers is that, as you can see here in the picture, that they are usually agglomerated. So the agglomerated polyethylene fibers clog the nozzle while printing and lead to the layer failure in 3D printing applications. So the objective of this study is to improve the dispersion of PE fibers within the cementitious matrix and enhance the flowability, storage modulus, and overall buildability by optimizing the mixing procedure. I will come and explain later in this slide. So the materials and proportions used in this study are typical for 3D printing applications. So we are using ordinary Portland cement type 1 at low water to cement ratio and polyethylene fibers at 1% per volume. And we used a hybrid rheometer to measure the shear strain versus time by applying pre-shear for 2 minutes, resting time of 5 minutes, and a frequency of 1 Hz for 180 minutes. Here we measured the storage modulus over time for hand-mixed fibers. We call it as received. I'm presenting here the effect of shear mixing on the storage modulus using different times. The storage modulus, as you can see here in this graph, increases up to 60 seconds and then mixes for longer time, up to 120 seconds, decrease the storage modulus, probably due to fiber breakage. Next, we evaluated the storage modulus evolution at different speeds. 800 rounds per minute is the lowest setting we have in this shear mixer that we used in this study. Increasing the mixing speed up to 13 or 18 rounds per minute was shown to reduce the storage modulus due to fiber breakage. As the lowest speed for the FlagTech mixer that we used is 800 rounds per minute, we also tried to use a Hobart mixer, the normal Hobart mixer, at lower rounds per minute, at 280 rounds per minute. It didn't work. These findings suggest that the optimal mixing speed for enhancing storage modulus of cement pastes reinforced with polyethylene fibers is 800 rounds per minute. Here, for SEM imaging, revealed that the additional mixing time at 120 seconds, as you can see at the right part of this slide, results in fibers with reduced aspect ratio. As shown in the picture on the left side of this slide, with 60 seconds mixing time, we observe that the fibers are intact in the cementitious matrix, and were compared to the chopped fibers sheared mixed for 120 seconds. And this is the reason why we see lower storage modulus. Then we evaluate the effect of storage modulus when adding few layer graphene nanoplatelets, exfoliated, to the mix with polyethylene fibers. And as we can see, a small amount of few layer or exfoliated graphene nanoplatelet increase the storage modulus by 1 order of magnitude. Here on the right part of this slide, you can see how the topological image through AFM is for exfoliated GNP and how ASM picture look like for the tri-layer GNPs. Another interesting observation concerns the rate of storage modulus increase during the first 30 minutes of storage modulus evolution. So we observed a much higher rate of increase of storage modulus, which indicates a rapid change of viscous to viscoelastic behavior, suggesting a higher buildability during the first 30 minutes of our experiment. These results are very encouraging for use of graphene nanoplatelets in improving the buildability and storage modulus in the mixes with polyethylene fibers. Adding well-exfoliated GNPs to the polyethylene mix that was shear-mixed for 60 seconds at the optimum 800 rounds per minute enhanced the storage modulus by 1 order of magnitude. However, our GNPs contains a small amount of superplasticizer. So we checked the polyethylene mixes with the same amount of superplasticizer. And by adding the same amount, we observed that we see a different effect with the addition of SP that lowers the storage modulus. And this is because the superplasticizer is freely available. Comparing with mixes that includes bulk graphene nanoplatelets, again, we observe the same trend. And as shown in this graph, you can see here with a purple color, the storage modulus drops by 2 orders of magnitude. The commercial graphene nanoplatelets consists of 15 to 20 layers and produce a totally different result with the storage modulus being much lower to the control mix. Therefore, the combination of few-layered graphene nanoplatelets in blends with polyethylene fibers, shear-mixed at optimum conditions, 800 rounds per minute and 60 seconds, give us the highest storage modulus. And here you can see how the AFM thickness of our as received graphene nanoplatelet looks like, and also the ACM image on the right part of this slide. We use values of grain strength to quantitatively evaluate the buildability of polyethylene fibers, reinforced mixes, and in general, high grain strength values indicate improved resistance to deformation, and which is a property that is essential for 3D printing. For the layers to be able to retain their own shape after casting. From the results shown in this slide, we observe that few-layer graphene nanoplatelet, as you can see on the right part of this slide, when compared to mixes with only PE fibers, have a great effect to the load capacity. And also graphene has shown an additional effect on the flowability. So as shown here on the slump values on the bottom part of this slide, the low water-to-cement ratios can be extremely low values in flowability and technically not acceptable for 3D printing. So the addition of superplasticizer only slightly improve the flowability, but still the slump values are beyond the 130 millimeter flow. And what we see though, however, with the addition of few-layer graphene nanoplatelet, we enhance the flowability, and now we are on the acceptable value of 142 millimeters. Looking at the overall results, we see a profound effect of graphene nanoplatelet on the buildability of polyethylene reinforced mixes. Addition of graphene nanoplatelets ensure adequate grain strength as well as sufficient flowability. The effect on the storage modulus, as you can see on the right part of the slide, is also equally impressive. However, the biggest effect that including graphene nanoplatelets exfoliated in these mixes besides the flowability storage modulus, lies on the enhancement of the green modulus of elasticity, where it takes more stress to cause the same amount of deformation. So, as we observed from the results of this slide, by adding a low amount of exfoliated graphene nanoplatelet, which is a control procedure after we tested the particle size, after we analyze all the parameters, increased by 30% the green modulus of elasticity when compared to mortar with polyethylene fibers overall. These results are very encouraging for use of graphene nanoplatelets in improving the buildability and storage modulus in the mixes with polyethylene fibers. And here we have to say that polyethylene fibers, when they are shear-mixed at optimum conditions, with the addition of the exfoliated graphene nanoplatelets, we saw the great potential, reinforcing potential that we have in our mixes when combined both two. And by that, I want to conclude my presentation, and I would like to acknowledge the financial support of the NSF Foundation Partnerships for International Research and Education, and the US Department of Transportation, the University Transportation Tier 1 Center for Durable and Resilient Transportation Infrastructure. I would like to thank my colleagues and my students and the students from our lab, and I would like to thank you all for your attention. And I would be happy to answer any question. Thank you.